These are electricity conceptual examples, number 21 through number 30. And in number 21, when we say an appliance uses electricity, we really are saying that the kinetic energy from the electrons is changed into heat and other forms of energy in order for that appliance to work. So if you have a toaster, when you plug that into the wall, into those two little slots, the toaster then generates heat on the inside. There's some coils, and that comes from the kinetic energy of the electrons. Same thing if you use a mixer or a hairdryer or anything else. We're using the electron kinetic energy and we're transforming it into whatever other energy we need in order to do some work. For number 22, if you plug an electric toaster rated 110 volts into a 220 volt outlet, current in the toaster will be twice what it should be. The resistance actually stays the same, so it'd still be 110, ohms, but your voltage changes, and because your voltage changes, then your current has to change too, and you'll see that your current goes to 2 amps, and that's probably too much, and it actually, quote unquote, burns up the toaster. For number 23, says the resistance of your dry skin is usually somewhere around 100,000 ohms. So it's actually very, very high. For number 24, electric power can be defined in three ways. It can either be current times voltage. So you'll see here power is current times voltage. It can be current squared times resistance, or it can be voltage squared divided by resistance. The reason we can do that is we know that V is equal to I times R. So if we want to replace the I, we can use I is equal to V over R, and we end up with, in this bottom equation, P is, remember, equal to IV. If your I is V over R, and you multiply that times 1 over, multiply that times voltage, then you should end up with V squared over R. And the one above it, we do the same thing, but this time, now we're replacing voltage. So voltage, we know is just I times R. So here we would have I times R, and we end up with I squared R. And then the top one is just self-explanatory, pretty easy. For number 25, says compared to a filament thickness on a 60-watt light bulb, the filament thickness of a 100-watt light bulb will be greater. You actually need a thicker wire to prevent the melting of the wire that produces the light and the heat. For number 26, power outlets in our homes typically have a potential difference of 120 volts. For number 27, a 60-watt light bulb and a 100-watt light bulb, here's those two light bulbs again, are both rated at 120 volts. So notice that the voltage is not changing. Which light bulb has the larger resistance? If we go back to our equation, P is equal to IV, and we know I is equal to V over R, we can then say that power is equal to voltage squared over resistance. So in essence, our power and our resistance, these two quantities, have an inverse relationship. So the smaller the resistance, the larger the power. So our answer here would be the 60-watt light bulb. For number 28, says a 60-watt light bulb and a 100-watt light bulb are each connected to a 120-volt outlet. Which light bulb has more current in it? From the equation P is equal to IV, we see we have the same voltage, so we should have a larger power, and therefore we have to have a larger current. So that one has to have more current in it. Number 29, in order to form an electric circuit, we have to have several things. First thing that we need that they show you here are wires. So here are the wires. We need a power source, and that's our battery. We need a light bulb or some sort of resistance, and we need to make sure that they all form a complete circuit, one that is not broken or open. For number 30, and this is the last one, in order for current to flow in a circuit, you must have a complete path, and we just talked about that just a little bit. So everything needs to form this loop, and it needs to be unbroken.